Why does music have 12 tones? That seems awfully arbitrary. Why not 11 or 13? To answer that, we need to have a look at some music theory. Tones with half or double its frequency are considered especially similar, and thus are named with the same letter, and distinguished by a number. Between a tone and its double, called the root and the octave, are other tones with specific ratios to each other. These make up scales. C, D, E, F, G, A, B, and C again. This is C major. From D in C major, we can make D major. But now there is the problem that E in C major is slightly different from E in D major, and the F tones are very different. Extending to have all scales of the tones in C major, it gets kinda messy. Luckily many are close, and the rest can be covered by introducing 5 extra tones, and boom, 7 plus 5 equals 12. And check this out, it's a piano. Thank you very much, and good night. But those fractions for tones also look arbitrary, you say. Yes they do. And now we get to the fun part. A tone in air is just a lengthwise pressure wave. We can visualize these waves as a function of their pressure, which gives us a sine wave. The closer the peaks, the higher the frequency. For some reason, we like when the peaks of tones align. We call this consonance, and conversely, tones that align less are termed dissonant. A measure for how aligning a ratio is could be the number of aligned peaks divided by the total amount of peaks. By this measure, we see that the ratio 1:1, called unison, has a similarity of 1. The second highest ratios would be halving or doubling, both of which would have a similarity of 2/3, since for every 3 total peaks, 2 of those align. In Western tradition, the fifth, or 3:2, is very popular. We see that this has 2 aligning peaks for a total of 5 peaks. There are also simpler ways of rating the ratios. A common theme is to limit the set of primes you may construct your ratios from. This is called the prime limit, where the set up to 5, the prime limit, would be 2, 3, and 5, and this is very common. Another way is to limit the amount of primes you may throw into your fraction. This is the power limit. To unify the different scales, we can even out the spacing of the tones so the ratios between each are identical. This is called equal temperament, as opposed to the perfect ratios called just temperament. This introduces some inaccuracy, which we get somewhat used to. This is C major in perfect ratios or just intonation, and this is C major in 12 tones equal temperament. There's not a lot of difference to notice, which is 12 tones equal temperament doing a great job. But listen to D in just intonation, and then 12 tones equal temperament, and now switching between the two. And now we're at the point where we ask, wouldn't more tones per octave drive down the error? Yes, it would, but besides the fact that we will have a lot of unused tones in the scale, we require a very high accuracy from musicians. Take the ukulele, for example. In 12-tone equal temperament, we have the left one, and in 24-tone equal temperament, we have the right one. There is significantly less space between the frets, the more tones we have. So while 24 wouldn't be totally useless, the dream of having virtually no error with a gazillion tones equal temperament is highly impractical. We will therefore penalize equal temperament systems for the amount of tones they use. We now have all we need for comparing n tones equal temperament. First we define our limits. Let's start with 5 limit in both primes and powers. Then we want to construct some fractions. Using only one prime, we can create a list with all possible fractions from only this. If we have 2 primes, we can get all possible fractions with the dot product of the lists. This can be generalized to any amount of primes using NumPy's mesh grid. We create the lists of powers of each of our primes. We give these lists as separate arguments to mesh grid using the asterisk. From there we can take the element-wise product and reshape to one dimension. In a similar manner, we can get the effective power value of the fraction and the harmonic cost, which is the total and number of peaks per aligned peak. We then compile lists of ratios and their costs using the power list to only choose ratios within the power limit. So far so good, but the ratios are very spread out. If they were all in the same octave, it would be simpler to compare equal temperament values. So we define a function taking the ratio and iteratively either halves or double until between 1 and 2. We of course also need the equal temperament sequences, which will be calculated as the exponents, as this allows us to measure logarithmic error, which is octave invariant, which is nice. We then want a function to calculate the log error, taking the ratio and transform it to its logarithmic value, and then take the error of the most fitting value in the equal temperament sequence. Now we can define a function to calculate the sum of the errors, taking the error for each ratio against an equal temperament sequence. Let's explore equal temperament up to 50 tones equal temperament. For a prime limit of 5 and a power limit of 2 and up till 50 tones, we see a clear winner, 12 tones equal temperament. For a prime limit of 5 and a power limit of 2 up to 100 tones equal temperament, we see that it actually requires 53 tones to outperform 12 tone equal temperament, and up to 100 tones equal temperament, 12 tones equal temperament still comes third. Increasing the power limit to 5 actually highlights the performance of 12 tones equal temperament. But when is 12 tone equal temperament not very good? Let's increase the prime limit to include 7, have the power limit be 2, and take the first 100 again. If we include 7 in our list of primes, 12 tones equal temperament suddenly falls into mediocrity, and now 31 tones equal temperament shines. So that is why music have 12 tones in equal temperament, because we hate the number 7.